Hey, welcome back to distance learning. This is section 3.9. No, it's not 3.10, simplifying exponential and log functions and finding the derivatives of those. So I'm going to share my screen here and we'll take some notes. There we go. I'll try to zoom in on these. On the top, we have some of these reminder rules about logs. We tried to go over those in that last lesson to hopefully help out a little bit. Natural log of e is 1. Natural log of 1 is 0. ln of a to the r becomes r ln of a. ln of a times b, we can expand that out to natural log of a plus natural log of b. Division really becomes subtraction. Remember, e to the natural log of x, that e and that natural log cancel out, and you're just left with x. And this one, e to the a plus b, is really e to the a times e to the b. So the two on the top, no calculus involved, just a little bit of a reminder. This a can move to the front, so it's a natural log of e. Remember, this natural log of e is 1, so it's really a times 1, which is a. For example 2, we want to simplify e to the 7 plus natural log of a. So that's e to the 7 times e to the natural log of a. Now, what simplifies here is this e and this natural log. Those are both the same, not the same, those cancel out. So we have e to the 7th times a. I would probably put the a in the front, call this a e to the 7th. There you go, no calculus involved. The ones on the bottom, again, are kind of a review of what we did yesterday and how to solve for y with those I do, you do problems. For this particular problem, if I have natural log of y equals 3t plus 5, we can take e on both sides. So this is e to the natural log of y is equal to e to the 3t plus 5. Those become exponents. Again, over here on the left, e natural log cancel out. Y is equal to e to the 3t plus 5. That's all you got to do on that one. If I move over here, solve for k, again, review of what we did yesterday, I would bring a natural log on both sides. Natural log of e to the 2k is equal to natural log of 10. Then remember, this 2k can move to the front. So 2k natural log of e is equal to natural log of 10. Looks like I have an extra line in there. Oh, wrong button. 10. Natural log of e, if you look at the rules up above, is really 1. So 2k is equal to natural log of 10. How do we solve for k? We divide both sides by 2. So k is equal to the natural log of 10 over 2. You might also see this written as 1/2, oh, forgot the 10, 1/2 natural log of 10. Those are our equivalent ways of writing that. So same idea. So let's get into some calculus. Let's get into derivatives. So I'd posted earlier today a filled out, complete set of rules for your golden ticket. So if it's easier for you to print out the one I sent, that's fine. If you want to continue to fill out your golden ticket, that's fine too. It's totally up to you. We have a few more derivative rules. So the derivative of e to the u, we've already discussed e to the x, stays the same and is really e to the x. But for e to the u, we have to take into account that chain rule. So this is e to the u times du dx. So that's the one that goes on your golden ticket or wherever you're keeping track of those formulas. So for example, 5, what's your u? Well, u is the sine of x. We've gotten pretty good. What's the derivative of that? Well, the derivative is cosine of x. So when I use the formula up above on the top of the page, dy dx is equal to e sine of x times cosine of x. Now, students always want to know, is there more to simplify? Is there more I can do? Nope, that's it. E sine of x times cosine of x. You could switch the order, they're being multiplied. Cosine of x times e to the sine of x. There you go. So let's come over here and see what example 6 is up to. Ah, this guy right here. Switch colors. This means multiply, so we're dealing with a product rule. All these rules just keep getting layered and layered and layered. So remember, it's f g prime plus g f prime. So dy dx, f is now x squared, g prime is e to the x, plus g, that second term, is e to the x, and f prime is the derivative of x squared, which is 2x. Now, perfectly fine, you can leave your answer like this. I know you're very concerned about what the answer should look like. You can call it x squared e to the x plus 2x e to the x. You can also look and see what's exactly the same with these. Well, what is exactly the same? They both have an e to the x. So what we can do is factor that to the front. dy dx equals e to the x, x squared plus 2x. Now, let me back up because you're probably thinking, hey, wait a minute, that's not the only thing they have the same. True, they both have an x squared and an x. I could have factored an additional x to the front. Mathematically, it's completely correct. However, if this asked me to find a higher derivative, the second derivative, this would require one product rule, f and g. If I had to find a second derivative, this would be a product rule and this would be a product rule. There'd be two product rules. And if I had 2x in the front, and then parentheses x plus 2, that's also two product rules. Not interested. So this answer is really the best one. Get that e term to the front, leave the polynomial alone. All right, example 7. I spy a chain rule. Nope, not a chain rule, quotient rule. So if we remember, dy dx is g f prime minus f g prime all over g squared. So the different pieces that go in there. G is the denominator, x. F prime is the derivative of the numerator, so this is going to start to look a little crazy. So it's e tangent x times the derivative of the exponent, which is secant squared, minus f, which is e to the x, tangent x. And g prime is the derivative of the bottom, which is 1, all over g squared, which is x squared. Goodness, that's a lot going on. So dy dx, how else can I write this? There's not really a whole lot to clean up, I'll be perfectly honest. X, maybe I'll move that secant forward a little bit, secant squared x, e tangent x. Just be very clear about what's an exponent and what is not, minus e tangent x, all over x squared. Now, I know you're trying so hard to make sure your answers look as good as they possibly can. And what I've seen on work, and it's not just you, it's not just this year, every calculus student, they see this x and this x squared and they try to cancel them out. You can't do it. The reason why you can't do it is because of that minus sign. You would have to be able to factor an x out of both terms in the numerator, and it's not possible here. If you really, really want to factor, I'm looking ahead, it looks like there's an e tangent x in both. So I can say, whoops, that's not going to work. We're learning here, we're learning. Dy dx is equal to e tangent x, x secant squared x minus 1 all over x squared. If you really want to factor, that's what you can do, but nothing will cancel after that. All right. Like I said, still learning. Okay, so let's come over here. This one's lots of fun. There is more than one way to do this problem. I have had students in the past find a natural log on both sides. Completely legal, completely valid, you can do it. Because this is an e to the u lesson, I want to practice that e to the u idea. So the derivative, and this has implicit in it as well, this one's crazy. Dy dx is the derivative of y on the left. E to the xy, we want the derivative is e to the xy, so that's e to the u. times the derivative of the exponent. That's product rule. So it's first times the derivative of the second. Need that dy dx for implicit differentiation, plus the second times the derivative of the first. Oops. Hit the wrong button. Now, when I look at this, I've got the dy dx. The problem is you have dy dx in two different places, and that's not going to work. It's here, and it's here. So we have to get those in the same place. We have to solve for dy over dx. So what you're going to do is say dy dx and distribute this piece to the first term and to the second term. So this is e to the xy times x dy dx plus e to the xy times y. Getting closer, we don't have to worry about parentheses anymore. But I still have a dy dx on the left and a dy dx on the right. We've got to get those on the same side. So I would take this term and subtract it to the left. Dy dx minus e to the xy x dy dx is equal to e to the xy times y. Awesome. Now, on the left-hand side, that dy dx, here's one, here's the other one. That's good. They're on the same side. So what we need to do now is factor those out. So dy dx, 1 minus e to the xy, x, is equal to e to the xy, y. If we were in class, I would say, what's the next step? What's the last step? We've done it over and over and over again. We're going to divide by that parentheses, that set of parentheses. So dy dx is e to the xy times y over 1 minus e to the xy, just scooch this over, times x. And that, my friends, is the answer. Now, if you did this another way, if you'd found the natural log on both sides, you might have a slightly different answer. And that's because e to the xy is equal to, this is where calculus gets a little fun, e to the xy is equal to y. So you can actually substitute the original problem back in. I know it seems kind of goofy. So you can also say dy dx is equal to y squared, y times y, over 1 minus xy, because this e to the xy is also equivalent to y. So two different ways to write the same answer. They are equivalent. If you get to this point, I'm thrilled, I'm excited, jump up and down, I'm happy, this is terrific. There's a smiley face. All right, good job. What else do we have? Natural log of u. This is another good one. These are probably my favorite derivatives. Can you have favorite derivatives? That's a pretty nerdy thing to say, favorite derivatives. So, natural log of u, the derivative is 1 over u du dx. These all have that chain rule built in. That's the cool thing about the du dx on the end. And that's the chain rule right there, built in. So let's come over here, number 9. U is the inside. It's x squared minus 1 inside the parentheses. Justine and I were talking about what's inside today. Inside the parentheses is inside. Du is the derivative of that. It's 2x. So when we find the derivative, dy dx is equal to 1 over u, so 1 over x squared minus 1, times du dx, which is 2x. So dy dx is 2x over x squared minus 1. I know, I just like that one. If we come over here, fun times. This one's a little bit longer for the u, but it's still inside. What is it inside of? It's inside of those parentheses. What color have we not used yet? We might use gray. U is cosecant x minus cotangent x. du is the derivative of that. So it's negative cosecant x cotangent x. The derivative of cotangent is negative cosecant squared, but it's already negative, so we're going to say plus cosecant squared of x. Whoops, got it right again. So when we go to put all this together, just have to write smaller. Dy dx is 1 over cosecant x minus cotangent x, cotangent, well, I guess I got rid of all that, cotangent x, times negative cosecant x cotangent x plus cosecant squared of x. Let's see, is there anything we can do to make this look nicer? Let's check it out. Dy dx is negative cosecant x cotangent x plus cosecant squared of x all over cosecant x minus cotangent x. Now, when I look at this, yeah, we did the calculus, it's all there. That's terrible handwriting. But is there anything we can do in the numerator? When I'm looking around, I see a cosecant here. There are actually 2 cosecants here. So I'm thinking I'm going to factor one of those out. So dy dx is cosecant x. We'll leave the negative in there. Negative cotangent x plus cosecant x all over cosecant x minus cotangent x. All right, cool. You factored. Now what? Well, check this out. I see some similarities. I see a negative cotangent x plus cosecant x plus cosecant x. So even though they're being added and subtracted and the order is different, that's okay, it doesn't matter. The entire quantity together, this whole thing in the numerator, this whole thing in the denominator are going to cancel out. So dy dx is equal to cosecant of x. Again, this is kind of bonus down here. If you got to this part right here, truly, I'm happy. You did the calculus. You did the calculus, and that's what I want for you, especially in these circumstances. I want you to go to your next calculus class and say, all right, I know what a derivative is. I know what the chain rule is. That's the important stuff. That nitty-gritty stuff about simplifying answers, worry about that next time. Just a reminder of the power rule. This is the first rule that I taught you. I guess it's the second rule. The first one was a constant. What's the derivative of a constant? 0. The derivative of a constant is 0. Hello. There we go. So if we're looking at the power rule, we've got dy dx is 3x squared. Nothing fancy. If we've got the next one, dy dx is 50x to the 9th. No problem. This one's a little bit messier. Dy dx, let me zoom in here a little bit. Dy dx is root 2 x to the root 2 minus 1. What? Yeah, that's okay. This piece up here on the exponent, this could be a decimal. You don't have to turn it into 1. You can leave it just as it is. If we look at this one, dy dx, bring the pi to the front. Pi is just 3.14. X pi minus 1. Again, you could turn that exponent into a decimal if you really, really wanted to. Not necessary. So those are all power rule. Nice, neat ones that we're used to and some kind of crazy ones. But what happens when I have an exponent raised to an exponent? And this is example 12. It's something you should see. I'm not sure that it's something I'm going to assess you on, especially because I'm not there in person to answer your questions in real time. These are my rules. Find the natural log of both sides, differentiate both sides implicitly, and replace y with the original problem. So here we go, example 12. This one's kind of pretty with the algebra that goes along with it, but I know that's also what makes it frustrating, is the algebra that goes with it. Are there other colors? Oh, look, there's more colors. All right, so we're going to find the natural log of both sides. Natural log of y is equal to natural log of x to the x. Find the natural log of both sides. Now, because of natural log rules, we're now, hello. My buttons don't like me today. I bet there's more highlighter colors too. Hey, look at that. See, learning new things here. This, we're going to now move to the front. So natural log of y is equal to x times natural log of x. Now this is an implicit differentiation problem. So the derivative of natural log of y, and we just learned it on the last page, is 1 over y. It's a y term, so we followed up with dy dx. Then the right-hand side over here, all of this is a product rule. First, derivative of the second plus the second derivative of the first. Looking good. So we're just going to clean this up a little bit. 1 over y, dy dx. X times 1 over x is 1 plus natural log of x. Now, remember, our goal is to solve for dy for dx. So what's in the way over there? That 1 over y. So how do I handle that? I thought I could move left. I'm going to multiply. What are we going to multiply by? You are going to multiply by y. So dy dx is equal to 1 plus natural log of x times y. If you come back over here to our rules, this very, very last step, replace y with the original problem. Well, we need to replace y with the original problem. So let's say dy dx is equal to 1 plus natural log of y, and I replace y with x to the x. There you go. I like those problems. They're a little much for us, again, especially with this distance learning, but it's definitely something that you should see. This is a long lesson. We have a few more examples to do. A to the u, you can actually use all of these steps and come up with the formula for a to the u, but you can also just take my word for it. Remember to jot all these down on that golden ticket or use that new one that I just sent to you. What other colors do we have? Oh, my own colors. We'll do that later. Let's use that one. The derivative of a to the u is a to the u natural log of a du dx. These are all being multiplied. Again, that chain rule is already built in. That's the color. There's our chain rule. All right, so what do? 2 to the x. These are fairly short and sweet. A is equal to 2. Your u is equal to x, that's the exponent, and the derivative is 1 dx. I guess du dx we say is 1. Get rid of that over there. Oh, too much. Okay, so the overall derivative dy dx is a to the u, so it's still 2 to the x. Natural log of a, natural log of 2. Du dx is the derivative, which is 1. What can you do to combine? I see some creative things every year, but unfortunately, none of them are legal algebra. That's the best you can do. I have students who try, students try so hard. They try to put this 2 with this 2. You can't do it. You can't undo the exponent, nor can you undo the natural log. So the answer that's in the box, that's really as good as it gets. What's example 14 got for us? Trig functions. So again, these questions that I'm asking myself, because I'm talking to myself right now, are the questions that you need to ask yourself when you do them. What's a? Well, a is 3. What's u? U is the exponent, cotangent of x. What's the derivative of u? Well, I'm going to find my golden ticket. The derivative of cotangent is negative cosecant squared of x. Put it all together into the formula. Dy dx is a to the u, 3 to the cotangent of x. The derivative of cotangent is negative cosecant squared of x. Is there anything to simplify? Not really. The only thing you want to be on the lookout for is this negative sign. If you have messy handwriting or you don't use the parentheses, and I've noticed a bunch of you don't use the parentheses, it could look like subtraction. So you want to move that negative to the front. Dy dx is negative 3 cotangent x cosecant squared of x. And there's our answer. I kind of think that's the end of the notes. How good's my memory? Oh, nope, not very good. Forgot one. All right, one more. Then it's the end of the notes. It's gotten very dark out. It's about 7:40 at night. Not quite in summertime weather yet. Let's do that one. There we go. Log base A of u. See this one sometimes, not all the time. The derivative of log base A of u is 1 over. Let's think about this one. Oh, I just had a total brain fart. 1 over u, natural log of A. Yeah, that's right. Du dx. The hours blend into days. The days are blending into weeks. 1 over u, natural log of A, du dx. And depending on what resource you look into, you might see these two switched around. Totally okay if they are. That chain rule, that's the du dx on the end. So what's A? A is 10. That's the base. What's u? The stuff inside, 3x plus 1. What's du? The derivative of that is 3 dx. So find the overall derivative, use that formula up above. 1 over u, 1 over 3x plus 1. 1 over natural log of A, 1 over natural log of 10. Du dx is 3. I keep putting the dx over there. We're not ready for that yet. One day, I hope to do integrals with you. So dy dx is 3 over 3x plus 1 natural log of 10. Great job. Okay, now we have the last one. What's A? A is 2. What's u? U is the sine of x. Du dx, the derivative of that is cosine of x. Again, if you have your golden ticket nearby, no shame. Clearly, I need mine tonight. No problem at all. Dy dx is the derivative of that, which is 1 over u, 1 over natural log of A. Du dx is cosine of x. Whoop. Look, I made a mistake. This is natural log of A. I said A, but I didn't put the actual A in. A should be 2, so this should say natural log of 2. Now, if I write this all together as one fraction, my numerator is cosine of x. Then I've got sine of x, natural log of 2. I can take this one step further. What's cosine over sine? It's cotangent. So dy dx is cotangent x over natural log of 2. But again, if you get to this, I'm very, very, very happy. No problem at all. All right, that means, I don't have my assignment sheet right in front of me. I think I left for you worksheet number 4. So those first problems, the 1 through 10, are going to mirror that I do, you do problem set from Wednesday. So all of these. These are not actually calculus. This is all pre-calculus knowledge too. This is where I want you to solve or simplify or what have you. Actually, those are the exact examples from the previous worksheet. Lucky you. This is the whole worksheet stretched out. I'm not sure what I assigned to you where. I'm working with another teacher, so I think I assigned for you this worksheet 4, but if you already have the answers, lucky you, don't worry about the book problems and just work through these as well. So if you do them twice, it's just extra practice. No problem. I'm totally fine with that. So these problems on the bottom of the page, that's where you get into the calculus. Those are all derivatives. And just looking ahead here at worksheet 5, same idea. The ones on the top, these are all pre-calc, just solve. Ones down here are calculus. This one's long and annoying. There's a product rule for the u prime. This one's super long and annoying. There's a product rule for the du dx. Don't be afraid to email. Take a picture of your work, email it to me. I'll write out something else and I'll email it back to you if having a hard time getting a Zoom schedule set up on a regular basis. But we'll get there, I promise. We're looking ahead at worksheet 6. This is that x to the x problem. We have to find the natural log of both sides first. And then we have related rates. So looking ahead, I think next week we're going to work on these word problems. We're going to break it down and do basically one type a day. And then we'll kind of have a review at the end of the week and some kind of assessment, but next week is spring break. So I think we only have 3 days of work next week, not 5 days. So I'll have to look at the schedule. I was thinking in the back of my head. So anyway, thanks for doing the best that you can out there. I know that this is challenging, very less than ideal, but the thing that's going to make this work is communication. So don't be afraid to email me. No problem. I'm here. I can check my email at crazy times when I can't necessarily Zoom. I'm trying to manage first grade lesson plans in Zoom and fifth grade lesson plans in Zoom at the same time. So go ahead. If you get stuck sometime, email me. I do appreciate the work that you're putting into this. I really, really, really do. There's my iPad. Let me know if you have any questions. Stop that.